Hello, everyone, and welcome to TLC, the Tom and Lonnie chat. I am Benjamin Moses, the Director of Manufacturing for AMT. I'm happy to introduce Tom Kerfis and Lonnie Love. Tom is the Chief Manufacturing Officer, and Lonnie is the Group Leader, Manufacturing Systems Research. Both are from Oak Ridge National Labs in wonderful, scenic Tennessee. Today's episode will cover a lot of additive manufacturing systems, pros and cons. As the audience, as you guys think of questions throughout the discussions, feel free to type it in the chat. The team behind the scenes will pull these questions and we'll ask these at the end of the talk. Tom and Lonnie, feel free to feed my brain with some additive manufacturing knowledge.
Awesome.
All right. Well, let's get this. Let's see. Let me get this going here in terms of sharing the screen. I think we should be going there. And so thanks very much for, look at that. It's supposed to be Tom and Lonnie, and I just got an updated version that got shifted back to Thomas, but you just call me Tom. Anyways, we're going to get going. The bottom line here, what we want to talk about today over the next 20 minutes, and then we'll run some Q&A. Basically, it's just like metal additive. I think everybody is somewhat familiar, although we've got some more, some pretty cool stuff coming down the pike in terms of the in terms of some of the polymer and the big polymer and so forth. But today we're just going to talk about metal and what are the different types of metal additive and, just some pros and cons and so forth, but a fairly high level perspective of this thing and perhaps a few gotchas. One of the things, of course, you think about in terms of additive is that people have printed out their plastic parts and you got a bunch of support structures. Well, that works out really well. If it's made out of plastic, you just break them off. Maybe not so good if it's made out of titanium and you're trying to break that puppy off and so forth. So what I'm going to do now is Lonnie is really our additive guru over here, and I'm going to turn it over to Lonnie for the next several slides. I'll jump in a couple of other ones as we get towards the end to talk about different opportunities in terms of additive. So Lonnie, over to you, pal.
Sure. So first off, really am excited to be here. I think additive is going through a transformation and a good one. As Tom said, there's a lot of opportunities, a lot of gotchas, a lot of great applications for the technology. As Tom said, back in 2014, we were part of the demonstration where we demonstrated the large-scale additive with local motors in Cincinnati Incorporated, and really showed that the sizes are getting different, are getting much bigger, the speeds are getting much faster. And I tell people there's really 3 killer applications for additive, and you'll see this through the demonstration or through this talk. 3 killer applications: tooling, and tooling. It's really, if you look at additive, what is it great at? It's great at making low volume, complex parts that have high value, and additive, that's what it really is excels at. And that's tooling. So there's a lot of different types, and we're going to talk about metal. There's a lot of different types of conventional metal additive systems. You have your laser powder bed systems. We'll talk about electron beam powder bed systems, binder jet, ultrasonic, and then direct energy deposition. So we'll talk about each of these, and they each have pros and cons. I won't talk too much about the ultrasonic. It is a solid state process. It's a room temperature process, but it really is in niche areas. But the main ones that are starting to get more and more adoption in industry are the laser powder bed, electron beam powder bed, binder jet, and direct energy deposition. Next slide.
Coming up.
So in terms of the laser powder bed, all of the powder bed systems, first off, one of the gotchas is you're working with powder. And for your typical machine shops, this is not a material that most will work with. And so you have to take certain precautions. And it's something that if you're going to get into powder bed, we're happy to talk to you. There's a lot of handling that you need to consider in terms of how to handle the powder. Facility requirements, H3 occupancy is something that most of the fire departments will want. So as you start going up, it's like that starts to raise alarm bells. But you can make exquisite parts with these powder bed systems. The most popular is laser powder bed, where you're taking a plate, you rake a layer of powder down, and you use a laser to weld your part layer by layer. So you'll rake, weld, lower, rake, weld, lower, and you'll subsequently grow these parts layer by layer by layer. One of the challenges is these are typically very slow. You're building parts at maybe a fraction of a cubic inch per minute or per hour. So making a fairly large part, making something that weighs on the order of 10 pounds, 20 pounds can take days to weeks. Now, if you're making, you'll see again, if you're making injection mold components, compression form components, it really is a good option to get near net shape. Your surface finish still isn't quite where it needs to be, so you need to do some post machining. Next slide. And you can do a wide variety of powders of alloys. You can do H13 tool steel, you can do titanium, you can do Inconel, but it's always just one singular material. So this is a relatively old video that kind of shows the process. You can make some fairly complex geometries. And so you're just moving around, welding that layer. One of the challenges with the laser powder bed is you're melting metal, and you're having very high temperature gradients as you're both in terms of across the layer and into the depth. You have these massive temperature gradients, and so that manifests itself as residual stress, which causes the parts to warp and curl. So you have to think about these things in terms of how you anchor that part down. You probably will need a wire EDM to cut it off. If you need to have really tight functional surfaces, you need to be able to add enough material, usually 20 thousandths to 30 thousandths extra material to machine away to get to your fully dense part. So again, there's just a lot. It's not just hit the easy button. It's not just hit print and go. It takes some multiple steps. Printing is usually only about 30 to 40% of the process. You have the design, you have how you're going to anchor it to the part, how you're going to heat treat it to relieve the stresses, machining it off, and then any final machining, and then calibrating that part from your printer to the machine tool that you're going to machine it with. And that's something that Tom will talk about in the hybrids. Next slide.
Yep, and just really another point out is this thing is embedded in a whole bunch of powder, so afterwards you've got to clean all that powder off, and a lot of times the person cleaning it off is going to have some protective gear, including respirators and so forth, because you don't want to be breathing in the powder. So there's a lot to it, but it's awesome. There you go, kind of doing a little bit of cleanup there.
Now, what you'll notice with that is you actually have a glove box on most of these systems, and what the positive is here, you can reuse a lot of that powder. So you're only paying for the material that goes onto that part. You're brushing the powder away. It goes back into the machine. They have processes for sieving it, for getting any big chunks out. So you can reuse a lot of the powder. But you noticed how easy that was to brush away. The other approach is, instead of using a laser, to use an electron beam. So this is kind of like the old cathode ray TV. When I tell students this, they're like, they don't know what a cathode ray TV is. But you're using electromagnetic fields to move that energy around and weld. And this is really fascinating. So next slide, I think we have some videos that show how this works. So much like the cathode ray TV, you can actually almost paint the surface as you go. So you'll see the raking on the top right. Those lines, it defocuses the E-beam and it's preheating the material, and then you focus it and you weld. The advantage to this process is it's very fast in terms of the welding. A part that may take you a week or 2 weeks to print in a laser powder bed system, it will take you probably a day to print in the E-beam, because you're able to weld so fast. The heat is spread out. You're able to move that energy around and spread the heat out evenly, so your residual stress is usually very low. They preheat the powder bed, so that powder bed on most laser powder bed systems, that powder never gets over, that's not melted, never usually gets over maybe 100 degrees C, 150 degrees C. With the E-beam, it's like 600 degrees C, 700 degrees C. So the advantage there is that your residual stresses are very low. You can make very complex features without worrying about the part warping or curling. The downside is that powder bed, when you're done, is 600 degrees C. So you're going to have to, that machine is going to have to sit idle for a day or two to allow that powder bed to get cool enough where then you can move it out and put it into a bead blaster. And what you'll see, this animation on the top is nice. You'll see it goes out into a bead blaster. The material isn't loose like it is in the laser powder bed. It's kind of sticky. It's stuck together, kind of like a cake. So it's going to take a technician another day to basically break up that powder, blow it off, and recycle it. But again, you can make exquisite parts with really good mechanical properties. The mechanical properties are approaching that of wrought. It's not quite at wrought. It's better than cast, not quite as good as wrought. But you can make a very nice near net shaped part when you're done. Next slide. So the third powder bed approach, and I call this the redheaded stepchild. Everybody gets excited about lasers and electron beams. Binder jet, you're gluing particles together. You have a binder that you're laying down. So you're doing this powder bed, but instead of welding through a laser or an electron beam, you're using an inkjet head and you're putting down a binder and gluing those particles together. HP, X1 has been making these systems for probably 20 years. In terms of industry, this one actually is used a lot for sand casting. There's companies that make jewelry with it. Of all of the processes, it's probably the least expensive of all the metal additive processes, but it still has a lot of steps. So you're using a binder, you're gluing these particles together. When it's done, again, you'll have technicians that are like archaeologists with brushes, carefully removing the part that's embedded in this powder bed. You'll then put it in a furnace. You'll center it. Now it's going to be porous. So you take this powder, it's packed together, but it's not fully dense. So because you haven't melted the material. So then you'll put it in a furnace. You'll center it together. It's now a porous structure. You'll then take a lower melt material like a bronze. The bronze is the typical that they'll do. And they'll put it in a furnace. The bronze will liquefy. They'll pull a vacuum, and it'll wick its way up through all the porosity. So you'll have a solid, like H13 tool steel is a good material, but you can have a bronze back infiltration so that you'll have a kind of a metal matrix composite with steel and bronze. There's other things you can do. You can do ceramics on this really easy. One of my engineers, Amy Elliott, she leads all our binder jet work. She says, you could print dirt if you wanted to, because you're just fusing powder together. There's a lot of work on the post-processing, but this is a room temperature process, so you're not battling residual stress. When you do heat it up, it's done in a uniform fashion, so you don't have to battle the warping and curling. You can also use, instead of back infiltrating through a liquid metal, you can do gas infiltration, chemical vapor infiltration. So you put it in a chamber, pressurize it, heat it up, and that gas will turn to a solid, so you can get a solid. Like for ceramics, it's great for ceramics. Next slide. Mm-hmm. Now again, great application is tooling, where you need to do like conformal cooling. This was a binder jet project that Amy had to make a core for an injection mold cup, and you could actually do these cooling lines. This is the beauty of additive. You can have very complex cooling lines so that you can circulate the fluid, get really good heat transfer. You can print it near net shape, then you bake it, then you densify it, and then you do your final machining. So you can see the tools, the inserts that are on the bottom right-hand side. So again, very low cost. It gets the time it takes to make this core was just a couple of days. It looks like it was probably a 3-day job, and the cost was about $700 for a fairly complex core for a tool. So again, that's why I say it's a killer application. You don't have to wait to get the billet. You can go straight from powder to your near net shape, independent of the geometry. The powder doesn't care. You're building it up layer by layer. So you go direct to printing from your feedstock, then center it, then back infiltrate it, and then machine it. You can get your tool, and instead of 6 weeks, you can do it in a couple of days. Next slide. So if you go back one more.
Yep,
so
sorry about that.
We have is all of these are based on powder. The powder is usually expensive, anywhere from $30 to $100 a pound. There's a lot of handling concerns you have. You're getting really fine detail, but you're left with you're very limited in the size of the parts you can make. The largest powder bed systems are typically on the order of 800 millimeters by 600 millimeters by 600 millimeters. Usually that's a big machine that may cost you a couple of $1 million. Most 3D printers, most metal powder bed systems are making parts that are on the order of 250 millimeters by 250 millimeters by 250 millimeters, so a quarter of a meter in scale. There's a lot of applications where additive, and this is where I think Oak Ridge and I'm really passionate about is large scale. So there's a lot of ways of making small things. There's not a lot of ways of making big things. Usually when you're making small things, you're going to make a lot of them. When you're making big things, you're not going to make so many. So we've had a big push on large scale metal printing. When we developed the BAM, the Big Area Additive Manufacturing, back in 2013 and showed it at IMTS in 2014, at that point in time, most polymer printers, again, made things less than a cubic foot in volume at a few cubic inches an hour. You used a wire as the feedstock. If you look at most plastic 3D printers, you have a filament that you're feeding in. It's expensive. That filament is usually on the order of 20 to 30 bucks a pound. So our big question is, well, get away from the pellet, or get away from the wire, go to a pellet. So you're leveraging the injection molding industry. Get away from a liquefier, a heated tube, go to a screw, so you get your deposition rate up. We're doing the same. So that really transformed the polymer additive, where now we can make massive parts. We can put down 100 pounds, 200 pounds of material an hour. You can load with carbon fiber, glass fiber. You can do all kinds of things just by making that switch from wire to pellet.
Yep, and actually I'll add on here just as a plug for upcoming TLC events. On Friday, November 20th, we'll be talking about BAM, the Big Area Additive Manufacturing, where you'll get the whole scoop on exactly how we went from sort of the big differences between that little desktop tinker toy you got on your desk, to some serious heavy duty large scale printing where we're printing massive parts.
So we're doing, thank you, Tom. So we're doing the same thing now with metals, but in metals, what's the big supply chain? It's welding wire. So we're going away from powder for the most part and going to wire. So now you don't have all the safety concerns in terms of handling powder. You can have wire. You can buy almost any type of wire, get it anywhere in the world. It costs a few dollars a pound. And so we have a partnership with Lincoln Electric on steels, and here it's targeted on making tooling. You can put down, right now we're putting down 10 pounds of steel an hour. You'll see the machine on the right called Medusa. It can put down about, right now, 40 pounds of steel an hour, but we're getting to get to the point where it's going to exceed about 100 pounds of steel an hour. That machine can make parts that are about 6 feet in diameter, 6 feet tall, putting down 100 pounds of steel an hour. This starts to get exciting. We also are working with GKN on titanium for aerospace, making near net shape, again, using a wire as your feedstock and some form of welding, either wire arc, TIG, MIG, or laser to do your welding. Next slide.
Okay, and then actually, just as before we go to the next one, so this 3-robot system called Medusa, you'll hear about that on Wednesday, March 10th. I love it. I'm just putting in the plugs here, man.
So this is an example of what, I mean, these were intended for production. We did a demonstration back in 2018 at IMTS of a die in a day, where every day we would print, machine, and put into service a stamping die. This is the killer application. Again, imagine being able to take your tooling time and compress it from weeks down to days. Costs in terms of cost, using a couple of pounds or a couple of dollars a pound for the feedstock, getting it near net shape, and then all you're having to do is your final finishing machining. Next slide. So we've done I hate the pun. We've done a ton of demonstrations. Again, we partnered with Lincoln Electric. They have a facility they're building up in Cleveland called the Beehive, where they literally have 20 or 30 of these machine tool or these robotic welding systems, and you're growing things near net shape. So on the bottom left, you'll see some autoclave tools that they're making. So they're printing Invar near net shape. So get away from bump forming, where you're taking plate and you're banging it to get it into the shape you need, and then machining it to net shape. Instead, print it layer by layer with the robotic welding systems. Get it near net shape. Usually you grow it over about 50 thousandths, and then you just do your final finishing machining. So again, taking that Invar tooling that usually is expensive and long lead and getting it down again to where you can make it in days. One that's really exciting for us right now is we have a project with DTS, Dynamic Tooling Systems, and this is looking at automotive tooling. And this, again, we're looking at how can you change the tool and die industry using additive manufacturing. So we have a project where DTS is working with one of the tier 1 automotive manufacturers, and we're making a hot stamp die. We're 3D printing a hot stamp die, near net shape. It has the conformal cooling inside. This one uses actually multiple materials. It's easy to do with these robotic welding systems. It has a 410 stainless on the outside, a mild carbon steel on the inside. It took about 4 days to print. It's for a B pillar on a car. We printed it out near net shape, delivered it to DTS. They're doing the final machining, and they'll put it in the production line. And our goal is to understand how much time and money did we save the tool and die? What influence does it have on the performance of the stamping system? But this will go into a production line. So we'll have a no-kidding, real-world demonstration of this technology. We have partners that we're working with that are commercializing the technology. Materials will be developed. So this could really be a game changer for the whole tool and die industry. Next slide.
Good. And so let me just, there's a little bit of lag there. All right, I can control my mouse over here. So just a couple more slides here to really wrap up some of the conversation. So again, as Lonnie was talking about, a lot of near net shapes. So really, you could almost think about a lot of the 3D printing and so forth, and particularly with metal, it's going to give you a form or the geometry. And the hope is it's just like if you're machining a casting, you want to make sure that your final geometry is located inside of that casting. It's the same thing in printing. And in general, what we see, in fact, I think we can get these guys going over here. In general, what we see is that we have the higher. It's just the inverse of machining, right? So when I rough, I'm taking off a lot of material. I have a little bit lower accuracy. When I'm putting down a lot of material, or I have a higher material deposition rate, so I'm putting down weld wire and so forth, you're going to see it doesn't look nearly as good as some of the powder systems, but you can get a lot of material down. What I'm showing here, actually, this is a hot wire. So again, as Lonnie said, typically we'll use maybe weld wire, and that's what we're doing here. So this is a wire feed type system. They also have blown powder systems. We'll show you one of those that we have over at MDF as well. But in this particular one, it's developed by Mazak, and you can see here in the upper right-hand corner, that's the infrared of actually printing the part. But what's cool about the 5-axis is when you think about printing, everybody thinks layer by layer. Well, here we're actually rotating the part, right? So we don't even need to worry about building the support structures. We can actually change, if you will, the direction of gravity. So it's a whole different way of thinking about how we might make things. A couple of things that I find kind of interesting here on this particular one, where you can see, I guess it's the one directly below this this cup-shaped image. Basically, we're doing, if you think about a constant surface speed, we're now doing constant deposition rate. So the wire is coming out at a constant velocity. So as we get to the apex of the sphere that we're printing, we've got to speed it up so that we can actually we can keep that surface speed the same. So we have a constant surface deposition rate. Then another one that we have here, I'll just show you this one. This is OKUMA, and basically this is a powder blown system. Now, a couple of cool things here. So they're putting down the powder. So now you can mix and match the powders. With the wire system, you've got one type of material coming down. Here we can actually mix and match powders. One of the things Lonnie mentioned was the fact that you can get warping. And part of the reason you get warping is, well, look, if I've got a hot material going down on cooler material, when that hot material cools down, it's going to shrink more than the hot material, tends to potato chip things up. But if I have two different materials going down, they have different thermal coefficients of expansion. So even if they're at the same temperature when they cool, they may have different types of contraction. What you can do with the powder system is start off with the base material, and then slowly, we call it functionally grading to the material that you want on the top. So now you don't really have this discontinuity in terms of materials. This actually is very cool, and we'll talk about this on actually our first program of the year in January, Wednesday, January 20th, rapidly repairing dies, where we can actually take a die, put it in the machine, we'll probe it, we'll machine the worn areas off, and then we'll rebuild that die. And you can actually rebuild the die with much harder material. So now your refurbished die is actually better than the original die. Now, there's a lot more to it, and that's why we've dedicated an entire program. We'll get the good Dr. Feldhausen, who's our expert at that, on board. And then again, that'll be early in the year on January 20th.
Yeah, one thing.
Yeah.
There's a couple of points on this that I think are important. First off, the hybrid's been around. DMG showed their first hybrid in 2014, I believe, at IMTS, but it hadn't really taken off. But a lot of that is just the complexity. And so this is an area that we really are, the Department of Energy, Oak Ridge National Lab is really investing in. We've got a lot of partners. So we're working with Mazak, we're working with DMG, we're working with OKUMA on the machine side. But more important, I think just as importantly, not more importantly, but just as importantly, we're working with the software companies like the Hypermills, the Autodesks. When you saw those videos, it's really cool to see this part moving around, but it's how do you do that? How do you program it? And so we really are working with these companies to try to develop tools to make it a lot simpler to work with. Because I think if we can get to the point where you can take a die, I love the die example, where I can take an existing die that's for a product that's no longer in use, but it's close. Can I take that die, put it in the machine, scan it? And we also are working with Zeiss. They're another one of our partners in terms of what's the right metrology. Can you probe it? But can I see where it's at, and then can I machine it and add material where I need it, take material away where I need it, and can I turn that around in a day? Can I take that existing die that's no longer in service and either build it up where it's worn down or reshape it into a new tool? It could transform the tool and die industry. So we really are excited about this technology, and it's scalable. This is one of the other things is these companies, they make thousands or tens of thousands of machine tools a year. If we can get to the point where this is a tool that the normal mom and pop shop can use, it could explode. This could overwhelm the additive industry just because we're leveraging the existing machine tool industry.
Yes, and I mean that's exactly right, Lonnie. And really, what you're seeing here, these are machine tools that have had additive systems incorporated into them. And there's some pretty cool stuff. One of the things I did want to point out on this guy over here, let me see if we can run it again. You're actually looking down the fiber optic of the laser. So we're watching that material go down as the machine is running, which is kind of fun. And as Lonnie mentioned before, and we will talk about Medusa. So here's just a little preview. So Medusa, which is our three robot system. And again, especially with when you're using robots, look, if I want to increase my material deposition rate, I can stick another robot in there. And so we've gone from one head to three heads, and we've tripled our rates. And what you see on the left-hand side is you see Medusa, all three of those robots, there's a big turntable underneath there. All three of those robots are building apart in a coordinated fashion. What you see over on the right-hand side is they're not coordinated together. They're working on different elements of a component. So again, some pretty cool stuff moving forward, and you'll see a lot of these as we move forward with the different up-and-coming shows. Just a reminder before we wrap up and go to the Q&A session, Wednesday, October 21st, we'll have Kyle Salibi, who's one of our gurus in the Internet of Things IoT, and it'll be IoT for manufacturing. So with that, I will ask Ben to come on board and do a little bit of moderating. Ben is very moderate, and so I think we're ready to roll here, Ben.
Awesome. Thanks for the presentation, guys. I learned a lot. Yeah. So we'll start off with some easy ones. So one, what's your favorite machine or application of additive? You went through a bunch of really interesting use cases. Just want to get your thoughts on, hey, what's something new and either machine-wise or an application that you would consider your favorite?
Well, like I said, I've been I'm unabashed about what the application to me is tooling. I love, because I think you can do it today. You can actually make money at it. You can have an impact. And the machine that has me excited, and this will piss off some of our partners, but I love the hot laser wire. I love the laser wire. I love the hybrid wire. I think mom and pop shops are great. They're very comfortable with machine tools. They're very comfortable with welding wire. What we're doing is we're saying, let's bring them together. It's not hard.
Yeah.
Awesome.
And so on my end, I mean, I agree with Lonnie, but I tell you, one of the things that I find cool, we haven't really talked about this, but what one of the machines was making, and it was spinning pretty fast. We were actually looking at, there was just a mock-up of a medical insert, let's say a hip replacement or a knee joint replacement. So here's what's really cool about that. So number one, is you go in for your X-ray. They do a little CT scan. The CT scan comes out in voxels. So a voxel is a three-dimensional. Think about a pixel 2D. A voxel is it's just a little block. So in 3D. Well, we can take those voxels and we can actually generate the CNC paths using partners like Autodesk. They've got PowerMill or we've got Hypermill and so forth. Generate the paths for that. And what I would say is probably not build it up from scratch, but you'd have a blank and then you could build it and machine it back accordingly. The other cool thing, though, is when you stick that part into our tomography system, so we're using Zeiss CT tomography systems, that output is in voxels as well. So, in fact, the whole 3D world links together, and you could really pretty rapidly turn around and say, yeah, we can customize and qualify. So all of this stuff, we understand what's going on. We know exactly how this part was made. We can not only build this thing, but we can tell you exactly how it was made. It comes with a digital passport. It's a genuine part. It is good to go. So to me, that's going to be pretty exciting stuff. But I think I'd really have to agree with Lonnie. He's my favorite one on the tooling part.
Awesome. Let's talk about surface finishes. Do you guys mind hitting on some misconceptions and truths about additive and 3D printing on surface finishes?
Well, so, if the systems coming out now are getting better and better at really good surface finish. You're getting, Tom mentioned overhangs. There's some that are getting much more better control over overhang angles. But if you have to have a Class A automotive finish, the finer the surface finish, the longer it's going to take. And so my perspective is, if we need functional surfaces, I'm going to machine it. I'm not going to worry about the surface finish coming off out of the machine. What I am going to worry about is how to rapidly calibrate it from one machine to another. And on these metal systems, you always are welding onto a plate. So use that as a reference. Know where you're placing this part on that plate and calibrate the plate from machine to machine. And then you can shuttle it back and forth pretty easily. And then you can get whatever surface finish you need. Now, that said, one of the areas we hired Scott Smith from UNC Charlotte joined us, him and Tony Schmitz, and they'll be speaking at some of these Sparks as well. One of the areas everybody talks about support for additive for doing overhang angles. Well, we also need to think about support for post machining, especially if you're doing thin-walled structures. How should you design this part such that you really are thinking about the whole flow from printing, machining, heat treating? How do you make it? You want to save as much time as possible.
Yeah, and I mean, I'll just sort of add on again to what Lonnie said. Look, the more material you're putting down, your material deposition rate, probably the lower the precision you're going to get. Well, I mean, we can get atomically, we can sputter material on an atomic layer, but it's going to take a long time to build up even the millimeter of material. So I think machining is still around. But the other cool thing is, look, and by the way, this all lives within its own little space, right? So is it going to replace casting? Look, if I only need to make 30 or 40 of these things, awesome. I should go with metal printing and so forth. If I'm going to make thousands or tens of thousands, you just can't beat casting, right? And so I think what this allows you to do, and I think this is very cool, is it allows you to scale up your production capability. So, you just don't go from a couple of prototypes all the way to a few thousand and you're casting it, and then you find out, oops, I have a little bit of a bug here, right? You can go from a couple of prototypes to maybe tens to maybe hundreds, and then say, okay, I've got a lot of confidence in my process, let's go. The other cool thing I have to say is we were talking to some companies, they're saying, could you make molds? Like you saw the die that was stamping out. Could you make one that lasts just, let's say, 90 days or so? Because the idea really would be, look, I've got a new product. We're good to go. We're ordering the dies, but it's going to take 90 days. Can we print up some temporary dies that'll last 90 days so I can start making my product now, get it out to the market 90 days earlier before my competition starts to ramp up and so forth? So there's a lot of cool capabilities.
I think this is a really important conversation to have, is that anybody that really is into additive manufacturing that's knowledgeable, our position is it's not going to replace traditional manufacturing. It's just another tool in your toolbox. Yep. There's areas where it could really help you out, but it's not going to replace a lot of the traditional. It's going to complement them.
Awesome. Yeah. And so we talked about kind of additive as a process, right? So we grow the part, and then we have to do some processing afterwards, and just using the base plate as a locating feature, and how do we support overhangs. Do you see automation supporting additive at some point? I mean, we talked about on some of the safety issues, but how do you see that progressing?
Yeah, so we have a project. I'll protect the innocent. If you look at the robotics industry, so my background was robotics. When did robotics take off? When did it just explode? It was really in the 80s. Tom, you can help me on this, but it was really in the 80s. And why was that? The technology got mature enough that you could put it in an automotive factory and it could help out in terms of production. And then it just exploded. So automotive is, to me, kind of how do you break into that? How do you get into full production? And there is movement about to look at additive for not really low volume, but high volume production. And automation is going to be the key. And so there's a lot of the automotive companies that are really looking at this and their tier one suppliers, that how can this transform their industry? And the key, you're absolutely right. We got to get the human out. When you looked at the binder jet, there's always a person that's like an archaeologist with a brush, removing that part from the powder bed. All of those powder bed systems, you got somebody that's doing manual. We got to get rid of that. You got to automate that process. There's still workforce. Workforce is now instead of 100 people working on one product, it's one person managing 100 of these machines.
Yeah, and in fact, actually, it's a good point. I just bring my coffee cup up because I could use this as a great example. So, what companies really want, they want to be able to, let's say I want to repair this turbine blade over here. To repair the turbine blade, I machine the tip off, and I weld on some material, and then I machine and blend it in the whole bit, right? Really, what a company wants is they want to be able to load that part into the machine and let it rip. But the reality there is now you've got a lot of throughput. So, the welder, there are a lot of jobs that are sort of rough and so forth, but you've got better throughput. Even this coffee cup, you want to machine this thing. In order to take a really long tool to get to the bottom, it just doesn't make you can see vibrating all over the place. It's a beautiful bell. So what you want to do is add a little bit, machine, add more, machine, add more, machine. You could work your way up so you don't have this big long tool hanging out there. But nonetheless, as Lonnie has pointed out, it's great, but the human isn't going away because there's still an awful lot that goes on with the human. What you're trying to do is just make their lives easier, taking away the nasty job. I know I spent a good chunk of time in automotive. The stuff the robots do, the humans really don't want to do, right? But they do have some cool jobs in terms of supporting robots. So there's a lot of good stuff going on there, but automation is going to be important. But the human is still there. The jobs are still there.
Yeah, I love Steve Jobs. Steve Jobs has a classic interview where he's talking about the computer and how the computer is he talks about how the condor is the most energy efficient animal. The human is way down on the scale in terms of energy intensity for mobility. But if you put a human on a bike, all of a sudden you're the king, right? You're the most efficient on a bike. And so he said, well, the computer is the bicycle for the mind. And I think additive is the same thing. All of these tools make the human more efficient. It's not replacing the human. It's making the human more efficient at what we do.
Awesome. Great. So let's talk this additive about small businesses. What are some steps that a small business could take to either build confidence or touch into additive? Because I feel like it's a scary topic when you talk about $1 million machines and some of the safety.
Well, so, I hate to jump. Tom, I don't mean to jump in front of you. But, there are easy ways to get started. And there's some ways you can use additive that a lot of people aren't really thinking about. So I mentioned tooling. The plastic printers are actually really good at fixtures, check fixtures. If you want to get into it, and if you haven't already, just go ahead and buy a low-cost polymer printer. Get used to the workflow of how you design something, how you build something. Have it for fixturing, for holding things. Another one that's really interesting is I saw Penn State was doing something interesting recently where you can print foam, you can print all kinds of things. Well, so think about casting. If you're going to do a low-volume casting, print a lost foam core that you can then pack sand around, pour your molten metal in, and get the part. You can also, so talk about big parts. If you're doing things like that, You can actually build it in sections and assemble it to be one monolithic piece that then you put into the sand core and cast it. So I think you just have to, there's easy ways. You don't have to go out and buy a $2 million, $1 million piece of equipment. It's good. These metal machines are not hit the easy button. So ease yourself into it. Buy a little desktop plastic printer, start playing around with it if you haven't done so already, and then start looking at creative ways that people are using it for traditional manufacturing.
Right. And the other thing we look at is some of our partners, they actually work with their customers. So there are a number of customers, like die repair, where they know they have somebody melting on metal, putting welding on the metal and so forth, and then machining it down, and they know that it's a very difficult thing and so forth. And so they work with them to try and tailor these things. And really the addition, it just depends. So typically one of the most expensive parts of these metal additive systems, and I'm talking the hybrid, is the laser. So depending on which laser goes on there and the capability and so forth, it may not be a whole lot. It may not be a whole lot more expensive, right? So you take a look at these types of things. The other thing I do think you do want to be very careful of is the or not so much careful, but just be aware. If you get a hot wire system, that is pretty easy to deal with in terms of environmental issues and so forth. Because basically, I go to MSC and order a spool of wire, and you go to the back of that machine, that hot wire machine we have from Mazak, and you just shove the wire up the back, and it's ready to go. Again, you don't just hit the go button, but at least you can load it up. With the powder machines, you've got to be very careful about loading the powder in. Probably have respirators on. Some of the powders can be fairly explosive and so forth. Titanium. Of course, I think everybody's afraid of magnesium. So if you use magnesium powder, good luck. But so I think that there are ways or approaches you could take to help move things forward that are, again, Lonnie's got some nice lower cost ones, but I think if you're investing in a machine, you think that there's a good opportunity, you talk to the vendor and say, hey, what are you thinking about here? And it's probably not a whole lot more in some instances to get that additive capability. And in fact, there are actually some systems that you have and Lonnie probably knows the company, Jason's, right? Jason Jones's company. They've got a bolt on for your machine that you can give
hybrid technologies. Yeah, I think because if you buy an additive machine and you're struggling to figure out how to use it, you're losing money. Or buy a hybrid machine that has a 5-axis CNC, I can still make money using it as a 5-axis while I'm starting to learn how to use additive. So I think this is why I really like the hybrids. Is a company can make money at it multiple ways.
Yeah, and it's interesting. Last thing for me, and then we'll go to Lonnie or Ben. You can go on to the next question. But I just think it's pretty cool. Lonnie I'm in complete agreement when Lonnie said, look, all these machine tool companies making tens of thousands of machine tools, so they already got it scaled. But the other thing is just rigidity. If you take a look at the 3D printers, you saw some of the videos and so forth. No way you're going to load a tool on one of those things and start hogging metal, right? And so it just is a very nice direction to go on this thing, and they do have a lot of background. Now, I tell you, the downside of putting a laser with a lot of power and heating it up and so forth, I think everybody knows heat is the enemy of precision in machining, right? So, nothing is perfect. So there's still a fair amount of work to be done there.
Awesome. So if we back up a little bit, Lonnie did touch on it briefly. Do you feel that the design tools and software are keeping pace to harness additive manufacturing?
Yeah, I think that it's now gotten to the point where the industry is big enough that the software companies are really paying attention to it. And like I said, I've mentioned Tom Feldhausen has a list of all the different software companies, but Dassault with SolidWorks and CATIA, Autodesk, Hypermill, all of these companies are digging in and trying to develop tools to make it a lot easier to use. Because that's the hard part. It's hard and easy. The one thing that's nice about additive is a high school kid. I've got elementary school kids that can program a printer.
Sure.
Machining is usually a lot harder because you're starting with a block of metal and trying to figure out reach and access and moving in. Additive, you're just going layer by layer by layer. That's kind of a solved problem for traditional 3D printing. Hybrid now, it's a different animal. And so, and especially if you're going to go out of plane. So a lot of the software companies are really stepping forward and trying to develop tools that the standard mom and pop machine shop can leverage for making it easy.
Yeah, and these tools are cool because look, if you know, I mean, Autodesk Fusion 360 is something that everybody is using. They're trying to make it. Now they still have Power Mill. Really, I think the really high end stuff we're still using Power Mill, for example. But I think you could drive some of that. But you know, again, I agree with Lonnie. When you're talking, and again, hybrid, not so much additive, but hybrid, because now. So first of all, it's not just layer by layer. You could be rotating things around. In fact, if you're smart about it, you saw that one part where we had this cup that kind of mushroomed out there. We had no support structures there because as we were printing it, we were rotating it over. So you've got to incorporate some of the machine capabilities and so forth. The other thing, and again, as I said, you've got, when I was talking about making the coffee cup, add a little, subtract, and so forth. That's really the way to go. But now, you know, the whole approach just explodes because, okay, how much do I add every time, and what does my tooling look like? And there are a lot more decisions to be made. But that's okay. Our computers are getting better and better. The other thing that I really want to point out, which is very cool with the additive part of it, is the materials. Everybody gets hung up on, I can make cool geometries and all sorts of great stuff. But as I mentioned before, you could do things like functionally graded materials. You could do some alloying, especially if you've got different powders coming in and so forth. Or if you're putting things down, think about, I can change conductivity. I can put down non-conducting material and then either electrical or thermal. Thermal is a big one. Cooling channels and so that you don't need special material, but I can or optical conductivity and so forth. So there's a lot of different things you can do by changing the materials around. You can get some pretty cool things going on. So now your design, your CAD and your CAM packages are now not only looking at geometry, but material characteristics, even things like direction of gravity. So it gets pretty complicated pretty quickly. And now throw in Medusa, where I've got 3 arms running at the same time. Holy cow.
So there's a good question. Ben asked the question about what's going to grow more, in-house approaches or metal additive as a service. So if you look at who the big dog is right now on like the powder bed, it's GE. But if you dig in a little, what you find is, how did GE get so big and so good so fast? Everybody points to they bought RCAM and Concept Laser, but you got to go back before that. And before that, they bought a machine shop. They bought Morris Technologies. And Greg Morris was a family-owned machine shop. You said in-house, and I love this. Greg Morris, back in the 90s, was out. He thought, man, these metal printers, this is going to be a game changer. So he bought a couple of EOS machines, and he struggled and struggled and struggled and struggled. And I've known Greg for probably 10 years. He's a phenomenal guy. He's now retired. One of the best additive guys I've ever seen. And he had what he called his law of 4. It took you 4 times to print something right for the first time. And so I think it's a hybrid here. I think that there's a big learning curve even today on the powder bed systems. And so I think there's a lot of service bureaus that are getting better at it. You have the GEs, you have others that are getting better at it, but there's a steep learning curve. Yeah. What I'm excited about is, I think that much like with the powder bed, there was this in-house expertise that exploded with Greg Morris and his company. I think the same thing will happen here. What I want to do is put the hands of this technology into some creative shops where they can invest and they can work at it and they can figure it out. We're working hand in hand, and we're trying to identify what's the killer application. At the end of the day, you got to make money. This isn't a science experiment. Companies need to be able to make money on these machines. And so for me, what I'm very interested in is, what is a technology that's coming out that the expertise level isn't going to be so high that a company can make money on pretty quickly. And I keep going back to it. To me, it's these wire-fed hybrid systems. Yeah. Material isn't that expensive. Make money on a CNC. You now can add that additive and learn on it. You could be making money doing your traditional thing while learning with these hybrids and with these low-cost materials. Again, you're using welding wire, not powder. So I don't think I'm answering it. I'm saying that you're right in both. I think that today on the powder bed for the really exquisite parts. There's going to be these service bureaus that are going to be extremely effective. You can work with them now, and you can get a metal 3D printed part now, especially on tooling, and get some experience. But what I'm excited for is, as these hybrid machines start to come out, machine shops, mom and pop shops, buying them and figuring out how to use them to be competitive and to have a strategic edge over their competition.
And I'll just add on the wire side, again, I want to really point out, man, it is so easy. I mean, people who have just dealt with powder, they come in, they take a look at our wire machines. The best part is walking to the back of the machine and just show them the spool of wire going in the machine. That's it. They're like, wow, you don't need anything. Now, that being said, I should point out, as Lonnie mentioned, some of these prints do take quite some time and so forth. So one of the things, again, over at our operations here that people are looking at is even the backup power supply and so forth. Because you could imagine if you've got a 2 or 3 day print going on, which look is okay, the machine's humming along and so forth, and that works. But if the power just a little glitch in the power, and it's reset time. And that's something that people think it's a little bit differently. Usually in your machine shop, you're probably not doing a 2 or 3 or 4 day cut on a part. It might be a couple of hours, but not that long. So I think that there's a fair amount of thinking over there. But in terms of the service thing, the other thing, I want to make 2 more points. Lonnie said, Greg Morris's rule of 4. It's not so crazy. Think about people out there who are running machine shops, right? If it's a complicated part, how many setup parts do you need to go through before you got it right? Hopefully not that many, but you're still doing some setup. So again, it's not the magic, hey, push the button and you're good to go. But the other thing that I really think could happen is, look, if I do have, and this is really heads up, people, if you buy 2 machines, 2 exact same machines filmed with the exact same powder and run them, you're going to get slightly different parts. They're not going to be identical, so forth. And that's because there are about 100 little knobs in there, so to speak, proverbial knobs, that you have to tune. And so one of the things that I see coming down is we're going to be learning. You've got a bunch of sensors in there, and you can learn, okay, yep, these are slightly different machines. You've got to tune the knobs a little bit, or maybe the powder is slightly different, between the 2. And so one of the things that I can see happening is these machines could really be running online, and you can get the machine for a relatively low cost, but somebody is going to supply you with the powder and the know-how. Okay, here's my part. I want to print it. I'm going to monitor it, and remotely, I'm going to make sure that those knobs are all tuned and so forth. So that could be another model that could come out. So it's sort of like, think about it, Uber, right? You get into the car. It used to be that taxi driver knew everywhere to go and so forth. Now you get in the car, the Uber driver still needs to know how to drive, but basically Google Maps pops up and tells her exactly where to go. In fact, even better than that, the real-time information from Google Maps, because you've got all these sensors all over the place telling you what the traffic looks like, tells her the best route to take. And I think that this is part of the direction that could really be happening with the additive and so forth as we move along. More on that when we get to IoT for manufacturing next month.
Awesome. And that Law 4 is very interesting. Back when I was an engineer, it took me 3 times to get a drawing approved. So I had the laws 3 for my engineering drawings. As we're winding down here, I think you kind of hit on it a little bit, Tom, but what are some adjacent technologies that need to mature to continue driving additive adoption? Is it software? Is it sensors? Is it more robust motion control?
So I think it's I think it's yes to all of those. On the motion control side, not quite what you might be thinking, because the reality is these are in many instances a little bit lower precision and so forth, and we're doing okay. In fact, the beauty about using the hybrid is you've got this awesome motion control system already in place to move it around. In fact, think about it. You could just put that head there, and if you had an XYZ table, you're good to go, right? So life is pretty good. But I think really in terms of the software and how to use it and the design and so forth, that this is all sort of good. The other one is really the modeling, because I think it's a little bit more. We have some great models on the machining side, and we're still working on the models on the metal side, especially when you really want to get control over the material quality. In fact, the cool thing, and I'll let Lonnie chime in, but a cool thing when he was talking about E-beam and controlling how you're doing it, it's actually not so much. I think we all know how to melt stuff. It's actually the cooling of it, right, that gives you your metal characteristics. So it's kind of funny, not even thinking about, melting, no problem, but it's how it cools that gives you your results. So Lonnie, your thoughts?
No, I think software is a big problem right now. The machines, especially these hybrids, you're leveraging a technology that's very mature, and you're just adding a feature to it, but the software isn't there yet for planning. As Tom said, the nice thing about additive, you don't have to be hyper precision. This is not high precision machining where you've got to be accurate within a thousandth. Your bead, your material you're putting down it's a blob, right? And so you're going to be machining it back. The precision is on the machining side, but it seems like it's the programming and making the programming intuitive. But I cannot think of a better group of people than the machine tool industry, who's been programming machines for 40 years, to really embrace it and figure it out. We just have to provide them a tool they can make money at.
Yeah, the difficulty, I'll just look, Lonnie's correct, 40 years, God, it might even be, it's actually about, I think in the 60s when some of the first CNC, right? So 60 years now. But the reality is, with these hybrid systems, they haven't been around. I know, Lonnie mentioned DMG came out, about 7 years ago, but still people haven't really been using them. So one of the things that our partners in the software area are just excited about is just that we're using the machine. So we use it, we're like, man, this piece of software, it's terrible because here's the problem that I have and so forth. So just getting some experience, which again, goes back to, you can get some low cost, try out some low cost, systems and get a feel for it.
We haven't really talked also about kind of what Oak Ridge's business model is, the manufacturing demonstration facility. And so we really do a couple of different things. One is we're working with the machine tool manufacturers on their technology. So all of these companies, when we say they're partners, they're putting their equipment in our facility, they're putting people in our facility, and that's great. But there's a complementary piece of this puzzle, which is we have what we call technical collaborations, where companies can come in, not the machine tool manufacturers, the end users, and at no cost, they can work with us to see how you use it. And so it's a win-win where we're working with a company, demonstrating hand in hand how to use the technology. And the machine tool manufacturer is benefiting because they're learning what their machine is good at and what they need to work on. Yep. And the company, the mom and pop shop, and we work from anybody from large OEMs down to tier 2, tier 3 suppliers. They're reducing their risk by trying it. I think this is critical, having these use cases where you have help, and a lot of these OEMs, the machine tool manufacturers, they can do this, but they're completely tapped out on making the product. And so this is one where we're the government. We are here to try to help you. We do love the machine tool industry. We really do love manufacturing. It's one of the only things that provides us national security, economic prosperity, and even now it's been manufacturing that's helping us with healthcare, right? Yeah. COVID has been a big eye opener that we have to reshore a lot of manufacturing.
And I do believe actually you're going to hear about in one of the Spark presentations. I always put these plugs in so our friends over at AMP are all happy. But there is a discussion on COVID and what some of the things we did with COVID. And just to follow on with what Lonnie said, so it's the users, it's the machine tool manufacturers, but also you heard us talk about our partners in the CAD and the CAM sectors. You heard about the metrology issues and so forth. So really bringing that whole ecosystem together over here to allow, to really figure out how it all comes together. Again, we've been machining for over a century, well over a century, maybe two. I don't know when you want to go back to some of the first lathes and mills and so forth. But the reality is we've really come a long way with the 3D printing aspects of it. Part of it is because we've really been applying some great engineering and some great science to it. And we're going to continue to do that and really move it forward. It's a hard problem, but we're getting some solutions there.
Awesome, guys. This is a great conversation. And thanks for enlightening the audience about additive. And I learned quite a bit through this. And, we talked about a wide variety of things, some machines, some equipment, some implications to the industry, and what are some challenges and hurdles. So thanks again. And a special thanks to the audience. Tom, do you want to give us a sneak preview of some topics that you guys will be covering in the next sessions?
Yeah, sure. I mean, I've already been talking about them, but let's go through it. We're really targeting about a monthly set of presentations for the entirety of Spark. In October, so October 21st, we've got IoT, Internet of Things for Manufacturing. We'll have our IoT guru, Kyle Salimi, coming in here to help us talk about it. So we've got a guest star, I guess, guest speaker on that one. Then BAM, as we mentioned, the big area, additive manufacturing, so printing big things. This will be polymer, but we've got all sorts of fun things going on in there. That'll be our Thanksgiving special right before Thanksgiving. Then as we move over into the holiday season and so forth, we're going to talk about using the neutron source. So Oak Ridge National Labs got some big science going on over here. If you think about X-rays, X-rays can only go so far into things. Neutrons can go further. And so we'll talk about some of the cool things. And by the way, it's not just about looking inside of things. It's about getting other types of measurements. So we'll talk about some really cool things with big science. And then, as I mentioned, Dr. Tom Feldhausen will be our guest in our January show, where we're going to be talking about rapidly producing and repairing dies. So you'll see some cool stuff going on there. Then we thought this would be really cool. I got to tell you, this is just really cool technology developed over here by Dr. Brian Post, concrete printing. And I don't mean we call it SkyBAM. It is not putting up a big gantry and putting down concrete. This is something completely different. If you want to think of it, if you can go Google it and so forth, but think about SkyCam at a football game, but now instead of a camera in there, think about a concrete nozzle spewing out concrete. We're going to be showing you some cool stuff there. And then the last one that we have scheduled, at least for now, depending on how popular we are, we may continue on, but at least for now in March, as we get to our last one, it's going to be Medusa. That's our 3-robot system. You saw it operating right in our last slide in our deck, and so that's a little bit further out in terms of future thinking, but we're making it a reality. Good.
Awesome.
Yep.
Awesome. That was amazing. Yep. And thanks again, and take care, everyone.
Thanks
All right. See ya.